Chemistry chapter 30 theory video 5. Now we are going to learn about low resolution NMR. So we discussed earlier what NMR spectroscopy is. Now we are going to discuss about NMR spectrum where it shows a single peak for each non-equivalent hydrogen atom. Now when you look at this, so here you can see CH3, CH2, OH. So there are three peaks here, 1H, 2H, 3H as categorized. So what you can see is the zero reference point on the x-axis is at the far end. As you can see here, it is at the far end. It doesn't start here at the central point. It is at the far end, as you can see. So the chemical shift sigma is on the right of the spectrum, and the shift increases in value going left, right? So there are three peaks of ethanol, H atoms in OH, that is 1H, then CH2 2H, and CH3 3H. So they correspond to those values. So the highest of the three peaks, the heights of the three peaks, they vary. Now that 2H and 1H, 2H, 3H, that range is not equivalent. That is, it is not, 3H is not 3 times the height of 1H, right? So that is clearly seen. And 2H is not 2 times the height of 1H. So that relationship is something that you must understand. So then the area under each peak will tell us the relative number of equivalent hydrogen atoms responsible for that particular chemical shift. So the largest peak will be from CH3, and the middle is from CH2, and hydrogen from OH gives you the smallest peak. So then when you take the relative areas, when you get the relative areas under the peaks, then we can understand how they correspond with the values. Now, for example, if there is a alkane, then the chemical shift would range from 0.9 to 1.7. Alkane means CH3, CH2, CH. 0.9 to 1.7. So just see whether there is something of that sort. 0.9 to 1.7. There is a range here. There is a chemical shift there. Then alkyl next to C double bond O, it would be 2.2 to 3.0. So you don't have anything of that sort in that. There is a relationship. They would give you a range. This table is not something that you have to remember, but you should be able to make reference and make a connection with them. So now 1.2 is caused by the peak at 1.2 is caused by CH3 hydrogen bonds, this alkane bond, as you can see, right? 1.2 is caused by alkane. Then we have somewhere in between, we have between 4 and 3 we have another peak. So it is a little close to 3.6. Let's see what is responsible for that. 3.6, 3.2 to this thing is going to be the P 3.7 is what they have taken, correspond to CH2 hydrogen atom range 3.2 to 4. As you can see here, 3.2 to 4, alkyl next to electronegative atom. CH2 is what is responsible for that, as you can see, CH2O. Then last one is the oxygen is attached to a hydrogen. Then that range is between 6 and 5, that is somewhere around 5.4, that is OH, as you can see from the chart, 5.4. something of this alkyl next to an electronegative atom 5.4 and attached to um, the hydroxide atom is what we actually try to figure out from that. So we can obtain that value because alcohol is here as well, here the 0.56, that part. So this is actually a relatable, you would be given some really easy connections to make, but if you understand this part, this particular part, then you would be able to do it properly. But if you have any doubts or if you need any clarifications to be made, please let me know, then I will explain it further. Now you'll have to do question number 5, but before that you will have to write down a note on this. Write down: low resolution NMR shows a single peak for each non-equivalent hydrogen atom using these peaks and a data table. We can identify the organic compound. So I hope you understood. If you have any doubts, please ask me questions and please try to do question number 5. Please do question number 5. If you have any doubts, please ask. Now we are going to high resolution NMR. Now in the first one, high resolution means, now in the first one what we had was, for each set of new environment CH3 or CH2, we had a single shift. Then in this table we saw that there are overlaps. Now for example, ROH is 0.5 to 6, but in there you can have, for at alkene you can have, then electronegative atoms you can have, next to atomic rings you can have. So all of these are present. So then how are you going to specifically know what it is? So for that you will have to carry out a high resolution NMR. The high resolution NMR is useful to specifically understand what they are when the NMR values overlap, and also when there is a heavy shielding of the hydrogen nuclei by many electrons that surround the atom, then the peaks will shift beyond their usual range. Then also we will have to use NMR to specifically understand what it is. So it gives us more information to interpret. It is in low NMR, one peak that appeared as one peak will have a cluster of grouped or closely grouped peaks, because these the magnetic fields that would be generated by these spinning protons will interfere with the neighboring nuclei, and as a result there would be more energy interference that is shown, and this interference that is known as spin-spin coupling. This splitting pattern of a peak will depend on the number of hydrogen atoms on the adjacent carbon atom or atoms, right? So you will have to look at the adjacent carbon or atom or atoms to figure out what is going to be present on the other set of information that have been provided. So number of signals a peak would split is equal to n plus 1, where n is the number of hydrogen atoms on the adjacent carbon atom, right? So now when you do the examples, you would be able to understand that. Now when you take the ethanol as an example, we have to use the n plus 1 rule to find out how many to find out the splitting pattern. Now CH3, now when you take CH3, when you take the chemical formula of OH, it is going to be CH3 CH2 OH. Now when you come to CH3, it splits into 3 because the adjacent carbon atom, that is CH2, will be joined only to 2 hydrogens. So as a result, we get n plus 1 equals 3 because n equals 2. So this is a triplet separation. Then when you take the CH2, its adjacent carbon is attached to 3 hydrogens as a result, because adjacent one is CH3. So as a result, n plus 1 is going to be 4. That means that the peak related to CH2 would split into 4 sub peaks. Then that is a quartet split. Now the OH peak is not going to be split because hydrogen atom is going to be constantly exchanged with H plus atoms of other ethanol molecules and any water present. So as a result, we say that one average peak would be produced. So these are theoretical things that we need to know. So those things, we have to know them if we are to identify what the chemical is. So we will have to either learn what they are, or they should give us that it does not show a peak. So then this table 30.2 will give us the different types of peaks that would be given to you at the examination, and the NMR spectrum that would be that would be given can be interpreted in a certain way. Now, for example, let's look at this 30.19 figure. This is the spectrum for ethanol, showing the splitting patterns of splitting pattern. So now, as you can see here, 1H. So this has, the first one has not shown any splitting. So as a result, we know that it is OH. This has split into 1, 2, 3, 4 points. As you can see, 1, 2, 3, 4. So therefore, it is CH2. Then this one has split into 3 peaks. Therefore, we know that it is the CH3 part, because the neighboring atom is what we look at. If the neighboring atom has 3 carbons, then the one before will have 4 peaks. I hope that made sense. So now this 30.20 here we have, let's try to figure out what this is about. Now they have given the absorption of energy here. So what you need to understand is how we identify a chemical by using the NMR spectrometer is by following these steps. The first step is use the sigma values, that is the chemical shift in ppm, to identify the environment of the equivalent protons. That is the number of H atoms present at each peak. So we have to remember that peak 0 is the TMS standard reference peak. Then we have to look at the relative areas under each peak to determine how many each type of non-equivalent protons are present. Then apply the n plus 1 rule to splitting patterns to see which protons are on adjacent carbon atoms in the unknown molecule. So then we put them together to identify the unknown molecule. Now, as you can see here, now this high resolution NMR spectrum will be of an unknown ester in a glue. So if we look at the worked example, then we will be able to understand what it is. An ester is used as a solvent in a glue. A chemist was given a sample of the ester to analyze. The NMR spectrum of the ester is shown in figure 30.20. Identify the ester. So we have to identify the possibilities of the 3 major peaks. that appear at chemical shift of 1.3, 2.2 and 9.9. So we have to go back to that NMR table that was given. We know that 1.3 ppm is here 1.3, that means this part. 1.3 is going to be the zero peak is not something that we take, that is the TMS peak, right? So then we take 1.3. As you can see, it 1.3 we have to write, we have to look at the table and we write what the possibilities are. So the possibilities are RCH3, CH2, RCH2, then R2 would be greater than CH. Then we go to the next one, it is going to be 2.2. Then the possibilities are H3CCO, RCH2CO, or R2CHCO. Then we have another peak at around 3.9. We find out using the table, using this table. Using this table, we figure out what it is. And then we write all the possibilities. That is OCH3, OCH2R, then OHR2. Then we use the relative numbers of each type of proton and we label each major peak to narrow down the possibilities. So the 3 ppm, 1.3 ppm is marked as 3H. 1.3 ppm is marked as 3H, and the 2.2 ppm is labeled 3H, and 3.9 is marked as 2H. Now 1.3 ppm labeled 3H, and that would be a triplet because it is next to a carbon atom bonded to two atoms. That is the reason why it has split into 3. 2.2 ppm labeled 3H and a singlet. It should be next to a carbon atom with no H plus atoms attached to it, because it could be a carbonyl compound. What you need to understand is that now this one does not say, this 3H here, it does not say that it is split into it has 3 hydrogens, is not what it says. This hydrogen is actually for this particular one. For this one, it doesn't have anything. It is not attached to any carbon. That is the reason why it is not split. That is the reason why it is not split. I hope that makes sense to you. Because we are looking at the neighboring atom. So then we will be able to in 3.9 ppm we label it as 2n and split into a quartet because it would be next to a carbon atom bonded to 3 hydrogen atoms, that is CH3. So we get we put this entire set of information together to get ethyl ethanoate CH3COO CH2 CH3. I hope that makes sense. It is a little complicated. If you did not understand, please read through this. If you did not understand, then let me know. I will explain it a little further. Then after that, you will have to go to question number 6. But before that, let's do a note on this. Write down high resolution NMR. In high resolution NMR, using the effect of spinning of the nuclei interfering with the neighboring nuclei, which provides a splitting pattern of peaks, within brackets spin-spin coupling, we can identify specific specific cluster of grouped peaks that are dependent on the number of protons attached to number of protons within H1 atoms attached to the neighboring carbon. Put a sign, write down number of signals a peak splits into equals n plus 1, where n is the number of H1 atoms on the adjacent carbon atom. So I suppose that you understood this thing. If you did not, please let me know. Then we will explain it. I will explain it further. Please write this down. Table 30.2. Then it will be easier for you to understand it as well, right? So, if the number of adjacent H atoms is 0, then the relative intensities of the splitting pattern would be 1:1. That would have only one peak. That would have only one peak. Then if it has two peaks, if it is a doublet, then it will have two peaks. As a result, you would know that it contains two. The next one would have three hydrogens. If there are three peaks, then it would be a triplet. Then the next one is going to have 4 carbons. Then if it has 4 peaks, then it would have the adjacent H plus 7 atom has the 3 carbons. So that is how it goes. That is how it 3 hydrogens. That is how it goes. I hope it makes sense to you. Yeah. If you did not understand, please please let me know. If you understood, please do question number 6. So please remember this. If there is a single peak, there are no hydrogens in the adjacent atom. If there is one peak, if there are two peaks, there is only one hydrogen atom attached to the next carbon. If there are 3 peaks, there are only 2 hydrogens attached to the earlier carbon. And if there are 4 peaks, there would be 3 hydrogens attached to the earlier carbon. That is how it changes. Please understand that. And that is the principle that we use to identify these things. Now, the reason why we have how we identify the number of carbons is by using this number of hydrogens is by using this mechanism. If you did not understand, let me know.